Okay, so 4.6, the title is Formalizing Relations and Functions. First box that we're going to talk about is a couple of vocab words that we need in our data bank here, okay? The first one is a relation. All right, so relation. The second one is domain. So these are all formal words that we're going to be using to describe functions. And then the third one that we need to talk about is range. And I'm pretty sure that you have seen these before, but maybe not formalized as we're going to do right now. Okay, so first of all, let's talk about a relation, all right? A relation is just any pairing of numbers. So most of the time, a relation is nothing more than an ordered pair. An ordered pair. So sometimes it's given to you as x and y, but you want to be able to just pair two numbers together. That's a relation, an ordered pair. You want an incoming and you want an outgoing. When you put them together, they get a relation. All right? So the book has it, a relation as a pairing of numbers in a set. That's basically all it is. We're going to refer to a relation most of the time as an ordered pair in the form of x and y. All right? Now, the domain. Okay? The domain are all the numbers that go into your function. So your domains are your inputs, are all the numbers that go into our function. For function notation, the domains are the x values. The x values. The domains are the x values. So if numbers go into a function, then numbers come out of a function. What do we call the set of numbers that comes out of the function? Well, we call that the range. Okay, that's the set of numbers that's the output. Okay, and we always call those the y's, all right? So as a quick little example here, if I give you this relation, 0, 3, 7, negative 2, 11, and 4, I have given you a relation. Give me the domain for that relation. It's the set of x values, so what would it be? So the domain would be the set of x values, 0, 7, and 11. What would be the range, the set of y values? What would it be? 3, negative 2, and 4. And collectively, the entire, this right here, counts as a relation. So for us then, if we have domain, if we have range, and we have relation, then we can define the word function using those three words right there. So for us, the working definition that we're going to use is a function is a special relation. Remember, a relation is just an ordered pair. It's a special relation in which each value in the domain is paired with exactly one value in the range. Okay? So a function using these three words is nothing more than this. It's a special relation in which each value in the domain is paired with exactly one value in the range. If this holds true, then we say that the relation is a function. I'm going to give you some examples of a couple of relations, and we're going to decide whether or not they are functions, okay? Okay, I've given you A, B, and C. I'm going to call the set on the left, that's going to be my domain. The set on my right is going to be my range. The set on the left is my domain. The set on my right is the range. The set on the left is the domain. The set on the right is range. So A, B, and C. So I'm going to tell you that there are three elements in my domain. Okay? And I'm going to tell you that there are three elements in my range, that first one. And I'm going to give you a mapping. So that element, the element in the domain, is mapped to the element in the range. Alright? This one's going to map down here, and that one is going to map up there. So the question I have for you is, does that picture represent the words of a function? Yes or no? Somebody says yes. Okay, why? Why is this picture verifying what we have up in the words there? Will, what do you see? What do you think?
Because it said that each value in the domain is paired with exactly one value.
Pair with exactly one value. Okay, so far so good. All right, let me give you another one, okay? Here is, I have two elements in my domain, right? And I have one element in my range. And then I'm going to reverse that. I'm going to give you one element in the domain, and then I'm going to give you two elements in the range over here for part C. Okay, so let's focus back on B. Let me give you the mapping. Okay, I'm going to give you this one. That's going to go there, and that's going to go there. And then for part C, this is going to go here, and that's going to go here. Okay, one of those is a function, and one of those is not a function. Okay, what I want you to do right now is decide which one is which. Okay, we know A is, so we'll say yes, this is a function. Okay, now we're looking at B and C. One is and one is not. Think about it right now quietly with your table, and we'll come up with an answer in a little bit. All right, I've heard some really good conversations, and I'm curious to hear what you think right now. Who has a guess or a statement for option B? Option B, right there. Daniel, what do you think option B is? That a function, yes or no? Daniel says that this is a function, so that must mean that you think that this is not a function over here. Is that true? Okay, can you explain why you think part B is a function?
It's because the definition says that the domain has to be paired with exactly one value.
Hmm?
But for C, it's paired with two values, and then D is both of them are paired with one.
Okay, so yeah, this is really important, all right? And you know what? You're absolutely right. The picture of part B is a function. The reason is because it actually does follow the definition, right? It says that each element in the domain is paired with exactly one element in the range. Now, that element might be the same thing, but it's mapped to only one, right? That's the whole point, is that it's mapped to only one. Okay, so I know exactly for a fact, I know exactly where that element is going to go, right? I know exactly what output I'm going to get. The classic example of a function is a vending machine, and we're all very, very familiar with vending machines, right? Have you ever walked up to a vending machine and seen option 1 is water, option 2 is Sprite, option 3 is Pepsi, option 4, 5, and 6 are also Pepsi, option 7 is Gatorade, right? So in the middle there, when they give you 3 or 4 different buttons, no matter which button you push, you still get a Pepsi, right? That's what B is illustrating right there. I could push the top one or the bottom one, I'm still going to get a Pepsi no matter what. Now, consider the opposite effect. Consider option D, or C, excuse me. If you push Pepsi and water comes out, well, that's not what you pushed, right? So that's what this one is saying, right? You push one entry, and there are two different outputs in your range. That violates the definition that we have for a function. So therefore, part C is not a function and part B is. And many, many Algebra 1 students mix those two up, okay? But you guys didn't. I'm glad that you didn't. You guys, is that pretty clear? Think of the vending machine option. I think it's actually really, really good. All right, here's what I'd like you to do. I've given you a relation. The relation has these ordered pairs in them, okay? What I'd like you to do is find the domain, find the range, give me a mapping, and tell me whether or not it represents a function. So domain, range, mapping, and whether or not it represents a function. Okay, so let me give you guys this. So let's go here. Here's the mean. We can do all this in one, okay? Here's the domain. All right. And then over here, here's the range. All right. What elements are in your domain? List them for me. What are they? You have 4.2. What else do you have? You have 5. What else do you have? 7. And what else do you have? 4.2. Where do you have that one? Okay. What's in the range? 1.5, 2.2, 4.8, and then 0. Okay, good. So now, let's do the mapping. So I've said the domain, I've said the range. Let's do the mapping now. According to this relation, 4.2 is mapped with 1.5. Okay? This relation here, 5 is mapped with 2.2, so 5 is mapped with 2.2. 7 is mapped with 4.8, so 7 is mapped with 4.8. And then 4.2 is mapped with 0, so this one gets mapped to 0 over there. Okay. From the picture, is this a function, yes or no? No, this is not a function. How come? Because The element in the domain, namely 4.2, is not mapped to exactly one element in the range. It's mapped to two. Therefore, it's not a function. Okay, quickly do this one on your own. Do part B. Okay, who wants to show me what they got for this one? Give me the domain. -1, -2, 4, 7. Good. That's my domain. Give me my range. What would it be? 1, 2, -4. Okay, good. That's my range. Give me the mapping. Where does 1, -1 go? 1. How about -2? 2. How about 4? How about 7? Function or not? Yes, this is a function, absolutely. All right, the next topic that we talk about is something, box number 4, is something called the vertical line test. The vertical line test is used when you're looking at graphs of functions. Graphs of functions don't necessarily have to be lines. They could be plots, like this right here, points on the plane. So I have graphed a relation, and we're going to use the vertical line test to determine whether or not this picture represents a function. Now, the way it works is you basically take your pencil and you hold it vertically, and you go from left to right across the x-axis. And if your pencil touches more than one dot at a time, it fails the vertical line test, and therefore is not a function. So I just like to draw I like to just draw lines. So as you can see right here, right, boom and boom, and then there's another one, and then here's another one, and then finally here's another one. Right here, can you guys see that the vertical line test fails at that point? Okay, many people get that, but they don't understand is why the vertical line test works. So, in order to help us understand and see it, do you guys know why the vertical line test works? Why? Okay, tell me why it works. What do you see? What are you guys seeing?
The -4 is paired with two different angles.
Awesome. Most people don't get that. That's awesome. Yeah, the -4, right? If I was going to write this point out, what point would that be right there? That one. -4 comma what? Negative, this looks like -1, right? -1, because that's -2 right there. Okay, what point is this over here? -2. So look, there it is right there, okay? The domain value has -4 is paired with, look, two different elements, -1 and -2. So for the input of -4, the output is either -1 or -2. Therefore, it fails. But notice that it passes everywhere else. But if it fails in one spot, it fails for the whole thing. So you say the entire relation is not a function. That make sense? Pretty straightforward, right? Okay. Let me give you some other quick examples. I'm going to use Desmos to help me out with it, okay? So you guys ever used Desmos before?
They make an app for that, right?
Yeah, they do. But I like this one better, okay? So let me give you this one, right? What if I gave you y equals, how about -x quantity squared, and then let's go, +5, okay? So now I have this screen over here. I'll move it around. What do you think, function or not function?
That's a function.
That is a function, right? How do we know?
Because none of the domains are paired with more than one.
Exactly, right? None of the domains are paired with more than one. Okay, what we're trying to do here. I'll give you this one, right? Where's my little slide? Can you do the slider guy? So the last thing that we talk about for functions in this 4.6 is the function notation, which many of you have already seen before. So when we take, for example, like y equals, mx plus b, just as an example, if we're going to write it in function notation, we want to think of it in terms of inputs versus outputs. So we replace the y with function notation f parentheses x, mx plus b. So the way that we read this is, we say, whenever we see that, we read this as f of x. So that's how you read this statement, the left-hand side, f of x. That's called function notation, all right? And it is in the place of the y, but it means slightly different things because we're talking about inputs and outputs. I don't want you to just say, oh, y is the same thing as f of x. F of x means that we have a function that we're relating. Y is just a single output, all right? So I don't want you to just say blindly that they are the same thing. They mean different things, okay? So if, let's say I have let's say that I have f of x is equal to 3x plus 1. Well, what does f of 0 actually mean? What does that mean to do?
Just substitute 0 for x.
Yes, it means that we replace a 0, replace an x with a 0. So that would be 3 times 0 plus 1, or that would just be 1. So now the ordered pair, I can clearly see the input was 0, right? The output is 1. So we can write f of 0 is now equal to 1. So I have an ordered pair 0, comma 1. A little bit different than just saying what y is, right? So the input value is that's function notation for us to do. Okay, so I want to give you one last little practice here as an example. Okay, so if I give you f of x is equal to negative 1.5 x plus 4, and I tell you that the domain is the set 0, 1, or 0, 2, and 3, and this is your domain, okay, how do we then find the range? Okay, I have a function. The function notation says f of x is negative 1.5x plus 4. I told you that the domain is only the points 0, 2, and 3. So the domain only has 3 elements. How do we then get the range? You plug each of those in. Right, exactly. So I'm going to figure out f of 0 is equal to negative 1.5 times a 0 plus 4. Well, that's just 4, so I get f of 0 is actually equal to 4. Therefore, the first element in my range is going to be 4. Okay? How do I get the second element in my range? I plug in a 2 and I plug in a 3. Okay, go ahead and fill in the other 2 elements of the range right now. Okay, do you guys get 1 and then negative 1/2?
Yeah.
Okay, so if I give you a domain and I give you a function, we can take each element in that domain and run it through our function using function notation and then produce a range. So 0 gets mapped to 4, 2 gets mapped to 1, and 3 gets mapped to negative 0.5.